Okay, let's get started here. We're going to talk about isomorphisms to kick this shindig off. So, first things first, and if you have questions, you can post them in the chat box. I'll be happy to take a look. We're going to let G be a cyclic group, and we want to prove that if the order of G equals n, then G is isomorphic to Z mod n. So, all of these will be kind of sketches rather than the formal write-up, but so our sketch of our proof. So since G is cyclic, what do we have? Well, G equals some a squared, so on and so forth, up to a to the n minus 1. And then you could also put a to the 0, but a to the 0 is the same thing as the identity, which we'll call e. Okay, we want to find a map that is both one-to-one and onto here. So the first thing that we want to take a look at is how can we map this? Well, let's take phi of G. Oh, and let me just, I said the remark, let me just make it here again. We want to send phi from G into the integers modulo n. What's a natural map that we could do? Well, one that's not too bad, we can just take phi of, remember all these are just a to some power, so we'll say a to the k, and that has to equal, well, we'll just let it be k, where k is in Zn. Okay. So, oh, and if you'd like, sometimes we write it this way, but for the shorthand notation, we'll just leave it as k for right now, just understanding that we're going integers modulo n. So now in order to do this, we got to show first that this is a homomorphism. So how do we show that that's a homomorphism? Well, all we need to do is just kind of go through a calculation. So we know that anything in G is of the form some a to the I, a to the j, right? And you have some operation here. We can put whatever we want in G, whether it's a star. I'm just going to use multiplication just because. So now if we want to take that, we want to try and show, the big question mark I'll put here, is does this equal phi of ai, and then since we're in integers modulo n, we are talking addition there, so I'll put in the addition, phi of a raised to the j. Now, with this in mind, we can go through calculations. So phi of a sub I, or a raised to the I, a raised to the j, that's phi of a to the I plus j, just by our properties of how these groups operate. And what does this equal? Well, this equals I plus j. And then, well, wait a second, I is just phi of a to the I, and j is just phi of a to the j. So we do have our equality. So we can erase that. So this line right here shows that it's a homomorphism. Homomorphism. Okay. So now moving forward from here, where do we go? Well, we want to try and show that we end up having this be a bijection. Okay, well, we use the fact of these a sub i's having n in our list, right? If you have 1 to n minus 1 and then you have that 0 up there, that makes n total elements. Hopefully we'll get 1 to 1 and onto. So we'll start with 1 to 1. And how do you show 1 to 1? Well, you assume that you have a phi of a to the I equaling phi of a to the j. Well, that means that all of a sudden we have I is equal to j, and remember we're talking mod n. Okay, so at the end of the day, what does this mean? Well, this means that I minus j, oops, is equivalent to 0 mod n. Well, notice all of our answers here we have being between 0 in n minus 1. And so the only way this can occur, if both of these values are in this list from 1 to n minus 1, that means I equals j, and I should have been careful here. This is technically a mod n, and this is technically a mod n. But we know that all these values are between 0 and n minus 1, so that means right here we have a to the I, not equivalent, equal to a to the j. And that's what we want to show. We have 1 to 1 now. So onto let z be in Zn. Well, then z is an element of, let's say, 0, 1, all the way up to n minus 1. Hence, and we're just reducing mod n, so that's why we can get away with saying that. Hence, a to the z is an element of G. Right? Then what we have is that phi of a to the z equals z, and hence we have onto. Okay, and so we have 1-to-1 onto homomorphism. That means that we have G is isomorphic to Zn. That's extremely important. So now we have, anytime we have a cyclic group, we can show that we have that isomorphism right away to this abelian group Z mod n. Okay, so it cuts down on our time anytime we have a finite abelian group. The infinite case, if we have an infinite abelian group, essentially that's cyclic, we're talking the integers. So you can drop the mod n, you just have the integers in that case. And you can prove that. That's not too bad. It follows pretty much the same routine in terms of what we did here. So now moving forward, where do we go from this? We're going to try and use that result. Lagrange's theorem combined with that previous result, let P be a positive prime integer, and we want to show that every group of order P is cyclic and isomorphic to Z mod P. So let's sketch this thing up. How do we actually go about showing this result? Well, it follows kind of in the same light of what we just did. First off, we have every group of order P. So let's start. Let the order of G be equal to P. And then we want to consider an element A in G such that the order of A does not equal 1. In other words, this is another way for saying A is not the identity. Okay. And so I'll try and touch on an example on the side here in a minute of where we have something that's not 1-to-1 or not onto for our mapping, and we'll kind of get into that in just a minute. So I do see the question here about can we see an example of something that's not 1-to-1 or not onto. That won't be too bad. We can do something real quick. So I'll finish up this problem and then we'll kind of cycle back to that problem. So if we take this, let order of G equaling P, we want to consider our A being an element of G such that the order of A is not equal to 1. Where do we go from that? Where do we go from there? Well then, the order of this cyclic subgroup generated by A has to equal P. And why can we say that? Well, Lagrange's theorem states that it must divide the order of the group. The order of that subgroup has to divide the order of the group. So since our P is prime, you have it's either 1 or P. That's it. Okay? Well, with that in mind, what are we stuck with? Well, it's not 1, so that means it has to be equal to P. And then if that is, well, notice what does that mean? Since the order of this element, the cyclic group generated by the element A, equals the order G, we have a previous result that says then G is equal to that cyclic group generated by A. Well, wait a second now. So we have G is equal to A, right? and A has order P, well, think of our previous result. What does that mean? Well, we have a cyclic group, has order P. We know any cyclic group, we'll go back real quick. If we have a cyclic group that's finite, it has to be isomorphic to Z mod n. Well, in this case, what is our n value? Well, it's P in this case. So by our previous result, G has to be isomorphic to Z mod P. Okay, so we have that, and we'll try and fit something in here. So an example, where we want a homomorphism that's not one-to-one or not onto. I'll do the one where it's just not onto first. Okay. But we'll have it be one-to-one. Okay, so that means every element has to be mapped to. Real quick off the top of my head, we'll try and do from the integers to the real numbers, and we're talking addition in both cases. And how we'll define this is phi of, since we're talking addition, x plus y equals just x plus y. You can check and see. Hopefully this should be a homomorphism and should be pretty clear. So if we have it equaling x plus y, notice phi of x, or here, I defined the x plus y part. Let's do phi of x equals x. In that case, what we have is phi of x plus y, let me illustrate this real quick, equals x plus y, and that's equal to phi of x plus phi of y. So we have a homomorphism. Okay. Is it one-to-one? Well, yes. If you have phi of x, or let me use this, phi of x1 equaling phi of x2, what happens? Well, you have, in this case, x1 equals x2 just by definition, so you have one-to-one straight away. So this means one-to-one, but not onto. Since no element maps to, let's say, just pick your favorite value that's in the reals and not an integer, square root of 2. You could have any other number if you want, for that matter. So not on 2 since you have no element there. So if you want to see one that is, let's do not one-to-one, but is onto. We'll see this map later. We'll map from the integers into Z mod n. And I will actually try and distinguish how this goes using the brackets for Z mod n. So we'll go phi of x equals the integer x modulo n. So notice this is not one-to-one. Since phi of 0 equals phi of, let's say, you can pick any multiple of n. I'll do 2n. You could do any other multiple, so whether it's n, 2n, 3n, 4n, negative n, negative 2n, so on and so forth. Both of these, remember when you reduce mod n, that's 0 and this is 0. But 0 will not equal 2n in the integers. Okay, so keep that in mind on that one. Onto let's say Q be an element of Zn. And then all we need to do is notice, first off, q has to be some integer. It could be reduced modulo n, but notice, just to give you something different that maps to it, m plus q is an integer. And the reason why we can say that, n, when we're talking z mod n, that has to be an integer. And then the q, we're assuming that's an integer here. And phi of m plus q equals just m plus q, but we reduce mod n, that's equivalent to just q. Okay. Now, I haven't shown that this is a homomorphism, but it's not too hard to show, and I suggest give it a try. See if you can show that this actually holds up, and you can just use the properties of when we're doing addition modulo n. It shouldn't be too bad. Okay, so hopefully that clears up the one-to-one, not one-to-one, onto, not onto sort of thing. And you can do maps that are that always actually are neither one-to-one nor onto. The easy map there, just map whatever two groups you have, map everything on the group on the left to the identity. And so that will always be neither one-to-one nor onto as long as you have another element besides the identity. So there's a way to actually see that kind of example there. And that will always be a homomorphism, by the way, too. Okay, moving on. So determine if there exists a group with elements A and B such that the order of A equals infinity, the order of B equals infinity, and the order of AB, however the operation is defined, equals 2, if possible. So what we're actually looking here now is direct products or direct sums, however you want to call it. So how do we go about doing something like this? Well, think about this. If we have to have, and Lagrange's theorem is kind of coming to our rescue here too. If we have a whole bunch of sets that are finite, we know by Lagrange's theorem that we must have the order of any element in there divide the order of the group. So if it's finite, all of a sudden we know that it has to divide whatever that finite number is. So in order for us to even talk about these infinite elements here, we have to have a group that has an infinite order. So keeping that in mind, let's look at the simplest group with infinite order, or let's look at the integers. Doesn't have to be the integers, but let's take the integers. And we'll take this direct sum or direct product, however you want to call it. We've mentioned both kind of in that regards. So we need to try and get to something that has a finite order. So we can't just have two things that technically have infinite order. That wouldn't quite work out for it. Well, maybe it could, but let's keep it simple for ourselves. Let's just look at Z mod 2. Okay? And when you think of elements, notice the order of the element 0, 1 equals 2, since 0, 1, and however we define this operation, I'll put plus here, but 0, 1. Now remember, this column, or the column, this coordinate I should say, is dealing with Z, versus the second coordinate is dealing with Z2. Okay, so 0 plus 0, notice that's going to be 0. I'm kind of abusing some notation here. But this is 2 mod 2, which reduces to 0. Okay, so we're fine there. That's our element that we want to aim for. Now we want to figure out how can we combine two elements that have infinite order, but get back to this. Well, so we'll let A equal, well, the nice part about the integers, if you take any element, let's say 1, 0, notice as soon as I start adding multiples of 1, right, so any k times 1, I'll never get back to 0 unless k is 0. So that means that this order of this element has to be infinite. Okay, in a similar manner, now we need to try and sum it up to where it becomes 0, 1. Well, notice in order for us to have that first coordinate get back to 0, we need a -1 here when we sum up those coordinates. And the good news is, if we take any multiple, k times -1, you're getting negative k, and the only way for that to get back to 0 is if it's equal to 0 itself, so that means it's going to have infinite order. And then the other coordinate, what we're going to need is 1 here. Okay, so the order of b is also infinite. So we have two elements of infinite order, and then if we take a, and as I said, we're kind of abusing, there's component-wise addition going on here. That should equal 0, 1, which we already know has order 2, right? Didn't have to be this element. We can do another example. I'll give you something else. If you wanted to do, say, the real numbers as a let's say multiplicative group of real numbers there, so that means you toss out 0, and we wanted to take that with, let's say, z10. We can do this as well. It's not too bad. If you think of an element of order 2, real quick example could be something like 0, 5. Notice we have a 0 in the first coordinate, so adding that up, not going to be a problem whatsoever. For the 5 part, well, when you take a look at that, if you add that up twice, you get 0, 10, and so 10 reduces to 0 mod 10, and so that means the order of this element is 2. Now we're looking for two elements. Oh, I wrote 0, 5. My apologies here. That's a big no-no, not 0, 5. That would be if r was under addition. In this case, it's multiplication. So since it's multiplication, the identity is 1. So I want 1 there, 1, 5. My apologies with that part. So if you have 1, 5, we got an issue. Now we have 2 for our order, because the order of this element, when you multiply it by itself, you're going to get, so here, let me write this operation this way. If I do 1, 5, and then I'll put a star here for the operation that's going on here, and another 1, 5. What does that mean? Well, that equals 1 times 1 in that first coordinate, and it should be 5 plus 5, and we're reducing mod 10 in that second coordinate. So this equals 1, and then in this case 0, which happens to be our identity. So rather than kind of hand waving here, here's the formal write-up. So now, and by the way, if this was r with addition, that's when I could switch it to 0, 5. Something a little more interesting here. Now, how do we get two values that have infinite order? So a will let b, pick your favorite real, honestly, as well, as long as it's not having some integer multiple, positive integer multiple times it, that gets back to 1. And so an easy way to do that is, let's just take this to be square root of 2. So if we take square root of 2 in the first coordinate, and then any two numbers that'll sum up to 5 at the ends from our two coordinates. So with b, if we choose, say, we'll keep it simple, we'll put 3 here. That means I need to have a plus b in that second coordinate, or when I'm saying plus, we're just focusing on the second coordinate. This has to be 2. Now the real trick will be, can we get a number here that also has an infinite order? Well, yes, we have 1 over square root of 2, and that'll do the trick. And the reason why, for square root of 2, integer multiples times square root of 2, you're never going to get to 1 again. So that means order of a is equal to infinity. And then the order of b, what happens here? Well, you have 1 over square root of 2, take integer multiples times that, you'll always have that square root of 2 in the denominator, it'll never cancel out, so that also has an infinite order. So when you look at this a, whatever our operation is, started with b, notice that would be square root of 2 times 1 over square root of 2, and then 3 plus 2 in that second coordinate, and so we have this equals 1, 5, which we already know has order 2, and so that would be our example. Hopefully that helps see how you can have some crazy things happen when we start looking at direct products. So moving forward, find a group isomorphic to H, which is equal to this, basically the upper right triangle where you have ones down the diagonal, AB in that top row, and then a 0 on that that second row, third column position. So how do we approach this one? Well, easy way to kind of see this is first to figure out the order of H, and that won't be too hard. So you can think of, if we're talking Z3, you can have A be 0, 1, or 2. Okay, and then you could have the B position be 0, 1, or 2. So if you have 3 possibilities in the A and another 3 possibilities in the B, what we know right out the gate is the order of H equals 9. Okay, so that cuts down our chase here. One other thing that we're going to do is we're going to mention, first off, we'll show that H is abelian. And not necessary, but just trying to let you see what's happening here. So just so you can see that H is abelian, that's not too hard either. If we take 2 elements, we just have to show they commute. So if I have 1 A, B, and then we'll do 0, 0, 1, 1, and put a 0 here, and we take another element in this form. So we go 1 C, D, 0, that's a C, don't let your eyes fool you, 0, 1, 0, 0, 0, 1. What does this equal? Well, we can go 1s down the diagonal. That's pretty easy. And if you remember your matrix multiplication, so this top row goes times the second column. So notice that goes C plus and then A times 1. So C plus A, or I'll write it as A plus C. And then in our next one we have D, and then so our first row times third column will give you D plus 0 times A plus B times 1. So we can write that as B plus D. And then you can check and see that this next one would be 0, putting it in that position. And if you reverse the process, it's not too hard to see. We plug all these in. 1AB, 0, 1, 0. Just doing out that multiplication, you get the same answer. So 1A plus C, B plus D, 0, 1, 0, 0, 0, 1. Okay, so we have, that tells us, and this is our sketch here, that shows it's abelian. It commutes. So now with it commuting, what does that mean? Well, that means H, so scenario 1, you have one of 2 scenarios. H is isomorphic to Z9, that's our natural one, or scenario 2, H is isomorphic to a direct sum of Z3s, or a direct product, however you want to say it when we're finite. Taking a look at this, remember we're dealing with Z3, that's going to come in handy right here. So keeping that in mind, let's just for shorthand notation, well actually we'll write it out. So if we look at 1AB 0, 1, 0, 0, 0, 1, okay, the thing that we'll look at is either scenario, we know we're going to have an element of order 3, right? And the question is how you can distinguish the difference into which scenario we're falling into is check, is there an element of order 9? Because there is an element of order 9 in scenario 1. Scenario 2 there's not. And so if we raise some general matrix in this form, what do we get? Well, when you cube it, and you can carry out this calculation, you get 1, 3A, 3B, 0, 1, 0, 0, 0, 1. But remember, we are in Z3 for our elements. So this is equal to, well, 3 times A, you reduce mod Z3. When I write in Z3, for each coordinate I should write. So you get the identity. And we know that we're dealing with some element, assuming A and B are non-zero, that it can't have order 1, so it has to have order 3. And notice we can't exceed that. This is the smallest value, we can raise it to a power. So the order of this element, 1AB, 0, 1, 0, 0, 0, 1. Do not confuse this with determinant as well. This equals 3 when A and B are non-zero. let me write it this way, A or B is non-zero. Okay, so the order of that element is 3, and that's a general element. So there exists no elements of order 9. And as a result, what does that mean? Well, that means our H has to be isomorphic to Z3, direct product with Z3. Okay. The reason I like this for people to see is because we actually avoid going through the actual isomorphism. We can work it out just by having, we know it's in abelian group, so we know what it has to look like, and then we can break it down a little bit further. So nice proof to avoid that isomorphism. So now we're getting into the stuff where we can use those theorems, build upon those, and start to get to some good stuff here. So let's take a look at our next problem. So this is a big one, and this is actually showing you it's a way to define normal subgroups. So we're trying to show that all of these statements are equivalent. So how do we go about doing that? Well, if we want to show that all these statements are equivalent, the way we do it is we show implication after implication after implication. Okay, and so the first one, you can go kind of in any route you want to. I'll just start with 1 implies 4, and we'll kind of keep a tally. I don't think we'll be able to fit all of them in here without having to erase some. So 1 implies 4. The reason why we have this, and then showing containments is going to be the easiest. We can do 4 if and only if 5, so that'll make our lives a little easier too. So if we do 1 implies 4, what are we trying to do when we have 4? So we're assuming 1's true, right? So AH equals HA for all A and G. And we want to show that if you have any element of this format for all A and G, then you have any element in this set is also in H. So first off, let little h be in some big H here, and consider let's say, so we want to show in 4 A inverse HA is contained in H, and consider, let's say, A inverse HA in this A inverse HA. Okay, so what do we want to show? We want to show that this little element here belongs to H as well. Okay. Now, since property 1 holds, what do we know? We know that in this case we have some essentially HA equal to some AH1, where this H1 has to belong to H. Okay, and why can we get away with saying this? Well, notice we have AH equals HA, right? So that means A times some element in H, it has to equal some other element, possibly could be the same, some element in H times A. Okay, so we have that property. Now, what happens? Well, we know H1's in there. Well, what do you think we're going to do? Well, if you take a look, hit this thing right here on both sides on the left with A inverse. So then A inverse HA equals A inverse A H1, which equals, those two are inverses of one another, so that becomes the identity, and so you're left with H1, which is an element of H. Well, if H1 is this A inverse HA, that means it's also an element of H. Okay, so that means our first, therefore, we have our A inverse HA is contained in H. So 1 implies 4 is done. Okay. 4 implies 5. So easy way to go about this one, a real quick proof of this, since it holds, since property 4 holds, for all A and G, rather than using A, I can say, notice this bottom statement is equivalent to X, H, X inverse is contained in H for all X in G. That's the same thing. So if you look at that last one, since it holds for all, let A equal X inverse. Then we have A inverse H A is the same thing as, in this case, if we have that, we have X inverse H X inverse, which is the same thing. X inverse inverse is just X H X inverse, and that's contained in H, right? So in that case, what happens? Well, if we have that piece, all we need to do is say, okay, well, how does this end up working out? Well, we have this X, H, X inverse, so we basically have proven that for any single one of these, we can plug in the inverse and get the other property. So we have that 4 implies 5. In a similar manner, 5 implies 4. Remember, and I can change this statement in statement 4 to X inverse H X contained in H for all X and G. It's just changing the name of the variable. That makes no difference. So in this case, we're going to assume just to make it easy, we'll go Y H Y inverse is contained in H. Oops, contained in H. For all Y and G. Since it holds for all Y, let Y equal A inverse this time around. And what happens? Well, if we let Y equal A inverse, then we have sorry, I'll try to capitalize that. Let Y equal A inverse, and then we have, in that case, A inverse H. Well, first let's start to write it as Y H Y inverse, and that's the same thing as A inverse H A inverse inverse, and that's the same thing as A inverse H A, and we know that this has to be contained in H because the original is contained in H. Okay, and so that's what we were looking for. So we have an if and only if statement in terms of 4 and 5. So right now we have 4 if and only if 5. Those two are equivalent, so that's taken care of, and we have 1 implies 4. So now moving forward from here, where do we go? Well, let's do so 4 implies 2 would be pretty easy. So we have this A inverse HA is contained in H for all A and G, and so we want to show the other way. So let's say we have that containment. We're going to start with let H be an element of H, and we want to show that that's in this A inverse HA. Then E inverse, which is E is the identity HE. Since the identity commutes with any element, this equals H, and we know that this has to be an element of our A inverse HA. Okay? Well, if that's the case, what happens? Well, it has to be the, in this case then, since we have this A inverse HA going on here, we end up getting our result of that H is contained in A inverse HA. And that's the result we wanted. Okay. So now moving forward, let's see, how can we do the other one? Well, let's do 2 implies 3. So assume we have AH, A inverse, or oops, did that backwards here. So we want to assume A inverse HA equals H. Then what happens? Then we should have A inverse HA, and then we can put an A inverse here. If we do that on the left and right, we have to just be consistent. So we can write it this way. But this right here, if we go A inverse, that's the identity. A inverse here, that's the identity. So what happens? Well, what you're left with is then that statement implies that H equals A inverse, which is exactly the result we wanted. So we're done with that one. To cycle this, so we went 4 implies 2, 2 implies 3. If we do 3 implies 4, what do we have? Well, in this case, 3 implies 4. That's kind of a trivial result. Or actually, let's make it 3 implies just to match it up. Remember, we can go to either 4 or 5. So let's go 3 implies 5. And this follows from the definition of set equality. If two sets are to be equal, you have containment both ways. So we're done with that one. Okay, so what are we left with? Well, we need to get back to 1 is basically what we have to do. And we can do that with, well, any of these really. So let's take a look at 5 implies 1. So 5 implies 1. We want to try and show that if you have containment here, well, actually we could work it another way. Let's use instead of 5 implies 1. Well, we could use, for example, we could try and do, say, 2 implies 1. That would probably be our easier route, but we'll do 5 implies 1 just for keeping this working on out here. So we have that this holds, this property 5, and we want to try and show that this is equality. So so we have let A times H be an element of this AH. We want to show that AH is also contained in HA. Okay, so then, since we have this containment, then there exists H1 such that AH A inverse is equal to H1, since we have AH A inverse is contained in H. Okay, so now how do we get that to be something of the form HA? Well, that's not too bad. Just hit this on the right, then AH A inverse A equals H1A, which implies that AH equals H1A, which is an element of HA. Okay, so we're done with that route. So that gave us the containment going this way. Now we want to get the containment going the other way. So let's say we'll use H sub 2 and H sub 3. Let H sub 2A be an element of HA. Then, oh, and by the way, we can also use, since 5 and 4, remember these two are equivalent, so let's just pull in 4 while we can. Then there exists H3 in H, such that we have, what would happen here? We can use property 4 and hit it on the left hand side this time. So we have A inverse H2A, which is basically following property 4. That should equal H3. Okay, and H3 is an element of H, and so the reason we can get away with this is since we have A inverse HA is contained in H. Now we want to try and show that it's on the left hand side, so all we have to do is go A inverse H2A equals A H3, which means, well, what does that mean? We have H2A equaling A H3, which is an element of AH, and we have our other containment. So notice with all these statements, what do we have? Well, we had 1 implies 1 went to 4, and 4 went to 5, and 5 went to 4. Okay. And then we had 5 and 4, well, they kind of went back to 1. Right? And then we toss in 2 and 3 in here. So 4 went to 2, 2 went to 3, and 3 went to 5. And so notice we've kind of made full circle here, and we're able to close this thing off. And so we have all these statements being equivalent. All of them mean the same thing in terms of they are normal subgroups. So that's all we needed to show, and we have our result right away. So hopefully that makes sense on those, how they all work out. Okay. Let's try and move forward to the next problem if there's no questions then. Ooh. So now we did all that work for all those different statements, and we want to determine if something is normal, right? A normal subgroup. That's what that symbol means right there, that little triangle sitting there. So we have the special linear group of 2x2 matrices with real coefficients, and then you have the general linear group of 2x2 matrices with real coefficients. So the special linear group, what does that mean? This is all the elements of the form A, B, C, D such that the determinant of A, B, C, D equals 1. What is this set? Well, this is a set of all 2 by 2 matrices such that the determinant of A, B, C, D is just non-zero. And why can we say that? Well, because it's invertible. Okay, so a set of invertible matrices. Okay, so where do we go from here? How do we show it? Well, we have to think back, okay, how do we show it's a normal subgroup? Well, you can show A times H equals H times A. You can show a whole slew of things, right? The easiest, what I would say, in terms of the approach, if you look, we have in our list here, showing equality, you have to show the two sets are equal. Sometimes that's nice, but I would say the easiest of two, obviously 2 and 3 require a little more work than what 4 and 5 do. And so you can pick whichever one you want, 4 or 5, and we'll work with that. So, let A be a general matrix in GL2R, and X, or let's call H, well, yeah, I'll use X to be an element, not to confuse it with that set H that we were talking about in the previous. So let X be an element of our special linear group. In order to show this, so in order to show it's normal, we wish to show that, and it doesn't matter which order you want to do it in, we'll go A inverse XA is contained, or not contained, an element of, I should say, because these are matrices, is an element of our special linear group. So how do we go about doing this? Well, we can look at the determinants. So notice the determinant of A inverse XA. You might be stuck, but you can actually do the multiplication if you want, but the easy way to know it is that determinants we can break apart. So this becomes a determinant of A inverse, and this is the determinant of X, and this is the determinant of A. And that equals, well, the determinant of A inverse is determinant of A to the negative 1, right, or 1 over the determinant of A. Determinant of X we'll just leave as determinant of X for right now. Determinant of A right here, and we can commute these things because these are all real numbers when it comes to our determinant. So determinant of A is 1 over the determinant of A. Determinant of A to the negative 1, I should say. And we multiply that by the determinant of A, and then rather than mark it out already, I'll write determinant of X. So determinant of A in times 1 over the determinant of A, that equals this 1. So 1 times determinant of X, well, notice X belongs to this group, and so that means the determinant of it has to also equal 1. So the determinant of this element equals 1, right? What does that mean? Well, if the determinant equals 1, it has to belong to the special linear group. That's an element of SL2R. Okay, so since we have that, what do we know? Well, that tells us that, so therefore, our special linear group is indeed normal in our set of invertible 2 by 2 matrices. Okay, that's all it is, pushing determinants around. That's all it takes to solve that one. So a lot of people get scared with these matrices. They're really not so bad when it comes down to it. So now let's move on to factor groups. So in order to talk about a factor group, you need a normal subgroup. Nice part about normal subgroups, you notice how you have right cosets, left cosets equal. So if you have any subgroup of an abelian group, automatically you have that that subgroup has to be normal. So this cyclic subgroup generated by 10, that automatically has to be a normal subgroup. And the fact that we're talking Z35, that's also a cyclic group. So we're basically finding this factor group, and this factor group of Z mod 35 by our cyclic group generated by 10 in that subgroup there. And you also hear me just say for short Z35 mod that subgroup generated by 10. So if you hear me say it that way, just understand what I'm saying there. But there's a few different ways to approach this. Now we'll go through a long way, and then we'll try and see how we can shorten this and really cut down our time. In terms of first things first, if we look at this subgroup, and this is not necessary whatsoever, we'll kind of illustrate why in a minute. So if you start listing down elements, you get 10, 20, 30. Remember, we're reducing mod 35, so the next one when you get to 40, that becomes 5, and then you get 15, 25, and then 35 is just 0. So notice 10, you have 7 elements listed. Now, just an FYI, we could have also, on the side here, the order of 10, right? We know Z35 is basically this group generated by the element 1. And element 1 has order 35. So this would be the order of Z35 divided by the GCD of, well, it'd be this element is 10 times 1, which, so that gives us our, what are we doing with our generator? So it's 10 in the order of the group. And so if we really wanted to have cut down on our time and without counting out all these elements, an easy way for us to have done this would be to take 35 divided by, well, the GCD here has to be 5, and so we get 7. A lot quicker if you know what's going on. Not saying it's horrible to do it out the other way, but if we get to big numbers, you're probably going to want to use this method over on the right hand side. It'll cut down your time drastically. So now we want to look at this 12 plus 10. Okay, so there's actually other ways to write this, by the way, but we won't focus on that just yet. So if we keep on doing this, so 12 plus this cyclic group generated by 10, let's basically add it with itself. Oh, there we go. What happens? Well, by factor groups, what actually happens is this thing is equal to, you can write it as 12 plus 12, and then rather than 2 times this cyclic subgroup generated by 10, it just combines into 1. That's how these operations happen to occur on the factor groups. So this thing equals 24 plus that element 10. Now this is going to be somewhat painstaking here, but we'll go through it and try and get our answer. So notice now, if we take 3 essentially times this, so adding up 3 of these, notice we can get basically the 10s just kind of combined together. So we're going to have that cyclic group generated by 10 all together there. This becomes 36, but when you reduce mod 35, you get 1, and so we're back there. Now, if you do 4 times 12 plus 10, notice once again we're having that 10 right there, and so you can just add another 12 to this, or you can do 48, which reduces to 13 plus our cyclic group generated by 10. And so now let's take a look at 5. What happens? Well, you can add another 12 plus the cyclic group generated by 10 here. So adding another 12 to this element gives us 25. And you might say, oh, we got to keep on adding. Well, actually you don't. Notice 25 is listed right here in our subgroup. So this thing is the same thing as 0 plus that cyclic group generated by 10. So what that means is the order of 12 plus the cyclic group generated by 10 equals just 5. Now, with that in mind, another way for us to have approached this, if we wanted to look at this element, first off, what is the order of this? Well, this factor group should match the order of the index here. Okay, so if we have this index, what is that going to be? Well, that's the order of Z35 divided by the order of this subgroup generated by 10. So that's 35 over 7. So this whole thing equals 5. Now, how can we go about doing this? Well, we know that the order of 12 plus this cyclic subgroup generated by 10 does not equal 1. And by Lagrange's theorem, or, well, we could do Lagrange's theorem if we make it a subgroup. That's not necessary, but so either way, we know the order of this must divide the order of what our group is. So hence, the order of our group has only 5 elements. And by the way, you saw them right here. For example, you had 1, 13, 25, which has become 0. So an easier way to have written this would have been, so the elements of this set you could do 0 plus the cyclic group generated by 10. The second one you could do is 1 plus the cyclic group generated by 10. Then 2 plus the cyclic group generated by 10. 3 plus that cyclic group generated by 10. And then 4 plus the cyclic group generated by 10. And that actually closes off all the elements, surprisingly enough. And so, for example, this 13, notice you could have written this as 10 plus 3 plus this. And so the 10 can go and jump right in there. And so this equals just 3 plus that cyclic group generated by 10. Same thing here. This becomes, the 24 case was the 4 plus the cyclic group generated by 10. Were there any others? We already had 1. And then 12, yeah, right out the gate, just this element is 2 plus that cyclic group generated by 10. Cyclic subgroup, I should say. But so back to our problem. What we actually have is that this, well, we know it either is 1 or 5, since that 5 is prime. So this thing must equal 5. And notice we didn't even touch any of this addition modulo this cyclic subgroup generated by 10, that element 10. So there's ways to bypass that and cut down on our time drastically. And I strongly suggest that we do that. That's going to help us in the long run in terms of finding solutions. So last but certainly not least, I want us to try and see how to work a normal subgroup and create kind of a Cayley table idea. So first off, find a group isomorphic to D4 mod H, where H is this E and R squared. What the heck does that thing look like? So in terms of what's going on here, you can remember that D4 is equal to this list of elements. We can go E, R, R squared, R cubed, and then we can do SR, SR squared, SR cubed, and S all by itself. Okay, so when we take a look at this thing, we got to find, first off, what the heck are these cosets involved with this D4 mod H, or this factor group of D4 by H. So with that in mind, the first one, the easiest one, H is going to be equal to EH, which is the same thing as, I do it on the left, actually considering we do a lot of the stuff on the class on the right, I'll keep that in mind. So we'll put all this stuff on the right. We'll use right cosets this time around. So we go H, and then we'll go HR squared. All of those are the same thing. They all equal a set E and R squared. Okay. So now with our next one, let's take a look. So let's hit H on the left by R, or on the right, I'm sorry, by R. So what happens there? Well, the first element, you go E and then R, so you get R. And the second element, you go R squared and then R, so that would give you R cubed, right? Well, think about another element that this might equal. And remember, cosets form a partition, and we're already assuming this is normal, so that shouldn't be too bad. But this is going to be the same thing as HR cubed, okay? And you can check and make sure that that works. When you go R squared and R cubed, notice it's R to the fifth, but the order of that rotation, remember we're talking symmetries on the square. If you have 1, 2, 3, 4, right? So if you rotate, so for the first case, rotate 5 times. Notice 4 times will get me back around to the start, and then one more would be that R, essentially. So that's where that comes from and why they're equal. Next one, let's do H and S. So what happens there? So this might take a little work, and we'll do that on the side. So notice you have, first off, S. That's not too bad. And then the next one, though, you have R squared S. You might say, uh-oh, what happens here? Well, the fact of how these dihedral groups work, this is S R squared, where R squared is the inverse term now. And so, but the inverse of R squared is R squared, luckily. So this is just SR squared. So we have S and SR squared. So what would that be? Well, it's not too hard to see that this is going to be H and then SR squared. Okay? So what happens with that? Well, in that case, just to try and see what happens, notice when you take the identity you get the SR squared, but just to show that when we go R squared and SR squared, what happens? Well, remember we just talked about R squared S equaling SR squared, so you can write this as SR squared R squared. Notice it's SR to the fourth, which is just the same thing as S, because it's S times the identity. So we have all those. Now what should be left with our partition, hopefully if we've done this correctly, would be, notice we've done S and SR squared, we've done H and HR squared, we've done HR, and so hopefully we have H SR. And what would that be? Well, so notice in the first case with the identity you just get SR, and in the second case, what do we have? Well, we should have SR cubed if we've done things correctly. And the way to check that one more time, just if you aren't familiar, R squared S and then R here. What happens? Well, in that case, remember we can flip those. That becomes S R squared. You usually can't, but in this case we can. And so that equals SR cubed. And in the case of H SR cubed, so what do we have? Well, the SR cubed, and then we have our R squared here. Notice that becomes SR squared R cubed, but R squared and R cubed, that becomes R to the fifth, which is R to the fourth times composed with the R, so our rotation there. So that's just SR. So that gives us back to our original starting point. So now there's all our elements, and rather than have repeats, right, because these are representing the same cosets, we only need to select one from each. And the easy way to do this, and we have a couple ways we can write. The first one, we can write H or HE or HR squared, but essentially this is representing our identity. So when we're actually doing the cosets in the Cayley table, what actually happens? Well, we have, in our first case, we have HE, and we'll put HE here. And you could write that as H. You could write it as HR squared. It doesn't matter, as long as we're consistent throughout. And I'm going to take the simplest looking thing that there is. So we'll have HE, we'll have HR in our next position, just because that's a little bit simpler too. And after that, what do we have? We have HS, and so we'll put an HS here. And then finally, HSR and HSR here. Okay. So the nice part, as we mentioned, this is the identity happening here. So if you take, first off, let me do HE. What happens when we take that composition? Well, this becomes HEE, essentially. And so we might be used to it on the left. The same thing happens on the right. We just move the H on over, and we're good to go. So that's HE squared, but the E is just the identity, so that just becomes H or HE, whichever you want to put. And since we used HE, we'll put HE right here. Okay. And for our next one, let's take a look as to what happens. Well, you can double check and see, and hopefully it's not too difficult. If we take HE and H, if I say it's any A, whatever A is, notice that becomes HEA, and so that would be just HA. So essentially whatever the second term is, we're reducing down to it. So that means that we have HR here, that means we have HS here, and we have HSR here. And likewise across this top row, we can write this as HR, this is HS, and this is HSR. Okay, so now where do we go from here? Now we're into the good stuff. And this is where it gets a little bit more interesting. So notice this next one's HR composed with our HR. So notice that becomes HR squared. But if you look, HR squared is the same thing as HE, right? And so this is just HE, surprisingly enough. Okay. In a similar manner, you can actually see all of these, and this can actually kind of tell you the isomorphism real quick. HS, if you look at HS composed with HS, that's HS squared, right? And HS squared, well, notice S squared is just the identity, so that's HE, and so we have HE in this position. Okay, and for our next one, let's see, what do we have? HSR. Let me write it. HSR and HSR. Well, notice that's the same thing as HSR squared. And anything with an S in it, whether it's we're doing rotations with it or not, essentially this becomes just a flip of some sort, whether it's over a diagonal or over any sort of scenario. So to give you an idea of what happened. So first, if you do the rotation, notice that would put 1, 2, 3, and 4. And then if we basically did a flip, so usually our flip is along this axis. So if we flip this along this axis, SR would look like 1, 2, and then we'd have 3 and 4 right there. Okay. So notice what that does is that just flips along, essentially, if we flip along this diagonal, notice that just does exactly what we wanted to do. 2, 3, and 4. And in this case, if you flip along this diagonal, notice you just swap the 2 and 4, which is what we did exactly. And so this has order 2, in case you didn't remember that. So this is just H in the identity right there. Okay. So moving forward for some other ones. Let's see here. That should actually give you an idea. Notice everything down that diagonal, when we compose it with itself, it all has order 2 for all those elements. And that's important, and hopefully that should give you the idea as to what group we might be isomorphic to. So our next one, let's see, what else do we need? We need HR and HS. So if we go HR and then HS, notice that's HRS. And we don't have anything listed as HRS, but the beauty of this is the same thing as HSR inverse, and HSR inverse is just HS, the inverse of R is R cubed. right? So SR cubed is just HSR, and you might say, oh, but Josh, we got another one to watch out, and we got to watch out our order. Well, actually no, because HS, HR is just HSR, and these two are equal. So actually, it didn't matter, they commuted. Right? That's the beauty of this. So when we have HS and HR, we have HSR here, and we have HS and HR. That gives us HSR here as well. So things are lining up nice for our Cayley table. Okay, so we only got a couple more, and hopefully they'll commute as well, because that'll tell us even more information as to what's happening. Okay, so we want to do HR and HSR. Okay, so with this one, what do we get? We get HRSR. Remember, we can flip-flop those around, so notice this becomes HS R inverse R, and so that should just equal HS. And if you wanted to see the other direction, hopefully it's not too hard to see. Notice this is equal to HSR squared, but remember HSR squared is the same thing as HS. We found that before right here, and so this is equal to HS as well. And so in that case, if we have HR and HSR, that's going to be HS, and HR and HSR is going to be HS. And you can probably guess what the last one's going to be, but just to show the calculations, I think it's good for you all to see when we're first learning about factor groups and things of that nature. Working this one out. So we're doing HS and HSR. Right, and hopefully we can see real quick as to why this commutes and what's happening there. So notice this is HS squared. R S squared is just the identity, so we have HR. That's not that bad. And then our next one, HSR and HS. I'm not saying we have to check it this way, but hopefully that hits the point home. So we get SRS, and then notice this becomes HS squared, our inverse, because we have to flip-flop these two. And notice that becomes just HR inverse, which is HR cubed, which you might be concerned, but notice HR cubed and HR are the same thing, so it doesn't matter. And so we are left with HR and HR. And so we have something that commutes, right? So we have an abelian group that has order 4. And notice the order of every element is either 1, as in the case of HE, or 2, as in the case of HR, HS, and HSR. So what that means is that this group, since it's of order 4, and it's abelian, and we have highest element, or highest order of any element is 2. We had first off, it was abelian, so Z4 or Z2 sum Z2. And since we have that the order of the elements at most are 2, that means that this is our direct product of Z2 with Z2. Okay, so hopefully that gives you an idea on how some of these examples work, seeing something a little bit more interesting with a factor group, how all that works and breaks down piece by piece. Obviously this is a lot more work that needs to be shown. There's actually tons of shortcuts here that you'd be able to work through. But hopefully the Cayley table helps you see what's going on with these factor groups and how those terms work. And if you have any other questions, just let me know, and wish you the best of luck on the homework.